last lecture, we considered an example of a uh, of a the rolling motion of a wheel. In that case, we analyzed the problem with respect to the center of the wheel. Now, today I am going to show that the but we say that is not necessarily that you have to always analyze the problem with respect to the center of the wheel. The reference point about which we are going to describe the rotation of the object can be anything. So, in this example, so there is a wheel which is rolls to the right without slipping, very important, and the center of the wheel has a velocity v0 which is 3 meter per second towards right. Now, locate the instantaneous center of 0 velocity and use it to find the velocity of a point A. So, a point A is this one. So, its location is at a distance r naught equal to 200 mm from the center O in a direction 30 degree as shown in this figure. The radius of the wheel is r equal to 300 meter. So, here is our strategy. So, the instantaneous in a pure rolling without slipping, this is the point where the velocity is 0. So, again just to remind ourselves, this is going to be our system and we are analyzing this problem in the lab frame, in some fixed origin frame in which this we see the wheel to roll. Now, first let us quickly estimate the angular velocity of the wheel. So, this we have done in the previous example in the last lecture. So, we are just going in the pure rolling without slipping. We got the relation that the omega times the ROC must be equal to V0. These are all magnitudes. So, this we learned from our last analysis of our last example. So, this gives the angular velocity which is same for all the points, assuming this wheel is a rigid body, is V0 divided by ROC. So, the V0 is 3 meter per second divided by ROC, which is 0.3 meter. So, that means omega is 10 radian per second. Now, if we take, so we want to write this velocity of the point A with respect to the velocity about the, so we are going to, so in the previous example we decomposed it as a velocity of a reference point O plus the relative velocity with respect to O. Today we are going to do it in a different reference point. So, the velocity of the reference point C plus the relative velocity of A with respect to C. Now, this is 0 in the left frame. So, all of this in the, so this is in the left frame, this is in the left frame and this is relative velocity with respect to reference point C. Now, that means it is a, if we analyze this problem with respect to C, it is just a pure rotation about C. So, then what is this? So, this is, so the A will move in a circle with radius AC. Now, how much is AC? Let us first get that. So, in this from this picture, so let us say if we draw a line here, from the vector we can estimate this AC using the vector analysis. So, from this picture it is clear that RAC, let us say, let us call it RAC. So, this is the vector RAC. So, this is the vector RCO, the location of plus the vector ROA. So, this is RCO, so the position of O with respect to C plus position of A with respect to O. Now, RCO, if this is my origin, this is x axis and this is y axis, then RCO is 0.3 meter times y hat. And RAO, how much is RAO? It has two components. So, this angle must be 30 degree from the geometry. So, it has two components. One component is ROA, which is so minus 0.2 meter cos 30 degree x hat plus 0.2 meter sin 30 degree y hat. So, let us call this as R, and let us call this. So, let us say R is equal to 0.3 meter and R naught is 0.2 meter. It is easier to write down the expression, and we will add put the plug in the numerical value at the end. So, then RAC square will be RCO plus RAO square, which is RCO square plus RAO square plus 2 RCO dot RAO. So, this will give us R square plus R naught square plus 2. If we take the dot product between these two, only the y component will survive. So, we have 2 R times R naught sin 30 degree, which is half. So, we have R square plus R naught square plus R naught. So, this is 0.3 square plus 0.2 square plus 0.3 into 0.2 square meter square. So, this will be 0.09 plus 0.04 plus 0.06. So, that is 0.19 meter square. Replace, that means this distance RAC will be square root of 0.19 meter, which is about 0.436 meter. This should not be a square here. So, then the velocity of A with respect to C is just omega cross R AC, and in the magnitude, if we look at the magnitude, so the direction is given here, but the magnitude is easy to calculate. It is just omega times RAC. So, omega is 10 radian per second times 0.436 meter, which is 4.36 meter per second, which is the answer. Now, let us take a very interesting another example of rolling motion. It is a very interesting example. So, suppose we have two objects, a solid cylinder and a solid sphere, both with the same mass m and same radius r. So, if we release them from rest at the top of an inclined plane, so there is an inclined plane, and from the top we are releasing this object. Which object will win the race? So, assume that the objects roll down the ramp, there is inclined plane without slipping, and there is a friction in the inclined plane between the object and the plane, and the friction is the same. So, in this case again we have a situation where these objects will have angular acceleration, which is given by alpha. Now, how to analyze this problem? So, we will see that the answer depends on this ratio, the I by mr square, where I is the moment of inertia of the object. So, what kind of motion is it has? So, in this case the natural choice is to look at the axis of rotation will be the axis of symmetry of the object, which is passing through the diameter, the diameter in the case of sphere, and the axis of cylinder in the case of cylinder, which is going into the plane into the screen. So, in this case we in our lab frame there is some translation and also some rotation. So, the motion of the object, the cylinder or sphere, is a combination of translation and rotation. So, the natural thing is to analyze it as a reference point as the center of mass of the and lab frame. So, we divide the motion into two parts. The first part is translation of the center of mass. The second part is the rotation of the center about the center of mass. Now, what determines the translation of the center of mass? So, this object is our system. So, on this there are two forces acting. One is the friction between the plane and the object, and the second is the gravity which is acting downwards. Then the net force, as you know, is, so the translation of the center of mass is determined by the net force acting on the system. So, the net force acting on the system is mg. So, we are taking this is the direction along the down the inclined plane. In that direction, the net force that is acting is mg sin theta minus the friction ms, and this determine the acceleration of the center of mass. Now, about the rotation about the center of mass. So, we saw, so the alpha is d omega dt. So, previously we got this relation. In this case, this is a particularly simple case where the angular velocity is fixed and passing along the axis of the object, and the angular momentum and angular velocity are in the same direction. In this case, so this moment of inertia, because we are looking at because the axis of rotation is an axis of symmetry of the object, hence it is a particularly simple case. So, we have this particular relation, and then the dl dt, which represents the torque on the object, will be given by the I alpha, and this represents the torque. So, what is the torque on the object? So, the torque on the object is just Fs times r, where r represents the radius. So, now you have three variables a, f and alpha. So, we need one more equation, and that is the condition of rolling without slipping. So, the condition of rolling without slipping is that a is equal to alpha times r. So, now we have three equations in three unknowns, we can solve it. So, the first thing is that if we eliminate alpha, we get so this is our quantity of interest is the acceleration of the center of mass down the inclined plane. So, we are going to calculate A. So, this is given by g sin theta minus Fs by m, and this sin theta minus, so the Fs from 2 we can write as I alpha divided by r and m, and from 3 we can write the alpha as A by r. So, we have 1 plus I by mr square times A is equal to g sin theta. That means A Cm is g sin theta divided by 1 plus I by mr square. So, the acceleration depends on several parameters: the angle of inclination, the strength of acceleration due to gravity, the moment of inertia of the object, the radius of the object and the mass of the object. So, there are several parameters, but they sort of combine to make a sort of this g and theta form a single group of parameter, and I, m and r square form as another single group of parameter. So, the acceleration is essentially given by two parameter, and this shows that the object with smallest I by mr square wins. Now, here I mention one interesting point, one interesting variation. Here we assume that the inclined plane is a plane. So, just go down in a straight line. What happens, but if you sort of think of something like a roller coaster game ride, then the path is not really a straight line, but or a plane, but it has some ups and downs. So, interesting variation is that if you start this cylinder and sphere from a same height and same position, and but the path becomes curvy, it has ups and downs. Then if you make the race, then which object will win? So, this is a interesting variation of this problem. There are several YouTube videos which sort of shows you this kind of demonstration, experimental demonstration, and so I invite you to search YouTube and look at some of those videos, and that will give you some interesting insight about this kind of problem. Now, we take a new different kind of situation, another very important class of problem we have discussed before. So, in earlier we discussed about collision problem. So, now we generalize the collision problem in the situation that now we allow rotational motion as well during the collision. So, the typical problem that example that I am having in mind is something like a ball hitting a bat. So, this is a simplified version of this problem. So, in this example, this is an example of an elastic collision with rotation. So, a mass m which is travelling perpendicular to a stick of mass capital so mass m came twice and length L, which is initially at rest. So, there is a stick of length L which is initially at rest, and there is a mass m which is travelling along this line, and it hits the stick at a distance, some distance h from the center of the stick. So, what is the location where it should collide elastically with the stick, so that the mass and the center of the stick move with equal speed after the collision. So, the new thing in this analysis, as we see, is that now we need to also consider the conservation of angular momentum. So, we have to the effect of rotation. So, let us understand what is the motion we are trying to analyze here. So, the motion that we are trying to analyze is that this mass m, a ball, comes and hits the stick, and after the collision the ball is continue moving in the same direction with some velocity v, and the velocity v will be now different from the velocity before the collision because of the conservation of momentum. The stick which was initially at rest will now start moving. Now, the motion of the stick is now a kind of, so it is doing some sort of a movement like this. So, this center of mass of the stick is moving with in a straight line, a translation doing translation along a straight line as shown in the figure, and the rest of the stick is actually rotating about the center of mass. So, by symmetry the center of mass is the middle point of the stick. So, let us analyze this problem. So, Again in collision, as we did in the collision problems, it is so our system is going to be the mass plus stick, and now since we involve, so this is our system. So the mass plus stick, and since we involves rotation, we must mention the frame of reference. So in our laboratory frame of reference, let us take this point as the origin. So origin in the left frame is the CM of the stick just before collision. So then before collision, that is just before collision, and just after collision. Now we are going to look at the motion of the system. Now in this case, it is clear that there is no external force acting during the duration of the collision. So we are going to ignore the effect of gravity in this problem. Just for the duration of the collision, if the collision time is very small, we can ignore the effect of gravity. This is our assumption. So then the conservation of momentum, and in any case, if we apply the conservation of momentum in the horizontal direction, there is no force in the horizontal direction. Also there is no torque, because if we take this as our origin, at the moment of hitting, the line of action of the gravity will pass through the stick, through the origin. So there will be no torque. So the momentum will be conserved, the angular momentum will be conserved, and since this is an elastic collision, the kinetic energy of the system will be conserved. So these are the three laws that we are going to use to analyze the problem. So note that there are three unknowns in this problem: h, where the mass is going to hit, the velocity v after the collision, and the rotational angular speed omega after the collision of the stick. So just before the collision, so if I apply conservation of momentum, we get the momentum of the system is mv naught plus 0, because the stick is at rest and the mass is moving with a velocity v naught. After the collision, both starts to move. Now the stick in the x direction, in this direction. So the mv is the momentum of the mass, and the stick. So we have to now look for the conservation of momentum, look at the center of mass. So the center of mass of the stick is moving with a velocity v, and if I apply, then they are equal. So this gives us the velocity, which is half v naught. Now what about the energy? Now let us apply the conservation of angular momentum. So what we get is, now with respect to this origin, the point mass, even though it is moving in a straight line, translation still have an angular momentum because of the definition r cross p. So the angular momentum is mv naught h. The stick was at rest, its angular momentum is 0. After the collision, the angular momentum of the stick of the point mass is, let us say, of mvh. So what is the angular momentum of the stick? So we are going to use our the rule that we have used is that this is the angular momentum of the center of mass plus the angular momentum about the center of mass. Now the center of mass is moving along this line, and this line is passing through the origin. So the angular momentum of the center of mass about this point is 0. Now, the angular momentum about center of mass is I omega, where I in this case, so this omega is clearly in the along our axis, which is axis of rotation is passing through the center of mass, middle point of the stick and perpendicular to the screen. So, we know from our this example that this I is m L square by 12. Now, the last is the conservation of kinetic energy, because it is a elastic collision. So, before the collision, just before, the kinetic energy of the mass is half mv square and the stick was at rest, and after the collision the kinetic energy of the mass is half mv square and the kinetic energy of the stick is again the two parts, as we follow our rule, that as if the whole mass of the stick is concentrated at the center of mass, which is moving to the right with some velocity of the center of mass. So, this is half m times v square and plus the kinetic energy of about the center of mass, which is half I omega square. So, now we can write it as, so half, you can cancel the half and m, half m v naught square is equal to m and v is half v naught. So, m v naught square by 4 plus m v naught square by 4 plus, so this half is cancelled from all the terms. So, this is m L square by 12 times omega square. So, that gives us the m L square by 12 omega square is equal to half m v naught square. That means m gets cancelled. So, we have omega, which is equal to 6 v naught by L. So, if we now plug it this value in this equation, from this equation now we get the m v naught h is equal to m v naught by 2 h plus m L square by 12 times root 6 v naught by L. So, we have m v naught h is equal to m v naught by 2 h plus m L square by 12 into root 6 v naught by L. So, m gets cancelled. So, we have half v naught h is equal to L root 6 by 12 L divided into v naught. So, the v naught gets cancelled. So, we get h to be L divided by root 6. So, this is the answer. So, now we have come to the end of this course. So, to summarize today's lecture, what we did is that we considered some example situations which involves translation and rotation together, and we also took an example of a collision problem. So, we generalized the collision problem to include conservation of angular momentum. So, I hope that you have enjoyed this course and learned something about nature, and also as this course helped you to increase your level of understanding about the mechanics problem, and most of all I hope that this course gives you some strategy to think about mechanics problem, so that you have now confidence to solve mechanics problem on your own. Thank you.